Welcome to DAR Tutors for online and home tuition. Today, we're diving into a fundamental concept in probability, the binomial distribution. By the end of this session, you will be able to identify, analyze, and solve problems involving binomial random variables. Specifically, you will be able to identify binomial experiments, construct their probability distributions, and calculate the mean and standard deviation for any binomial distribution. First, let's explore the core characteristics that define a binomial experiment. There are 4 key properties we look for. Let's remember them using the acronym BINS. First, B stands for binary. This means that each trial has only 2 possible outcomes, success or failure. For example, a coin toss can result in heads or tails, and a student can either pass or fail a test. Next, I is for independent trials. This means the outcome of one trial has no influence on the outcome of any other trial. Rolling a die multiple times is a classic example of independent trials, and stands for number of trials. In a binomial experiment, the total number of trials represented by n must be fixed in advance. You must know how many times you will perform the experiment before you start. Finally, S is for same probability. This means the probability of success, P, remains constant for every single trial. For a fair die, the probability of rolling a 6 is always 1/6. Let's summarize. For an experiment to be binomial, it must have a fixed number of trials. Each trial must be independent. There must be only 2 outcomes, and the probability of success must be constant across all trials. We'll denote the number of trials as n and the probability of success as P. The probability of failure, QQ, is simply 1 minus P. Let's test our understanding with a few examples. We'll decide if each experiment is binomial and explain why or why not. First is tossing a coin 100 times, where the variable is the number of heads, a binomial experiment. Let's check our BINS conditions. Is it binary? Yes, it's either heads or tails. Are the trials independent? Yes, one toss doesn't affect the next. Is the number of trials fixed? Yes, n equals 100. Is the probability of success heads the same? Yes, p equals 0.5. So, yes, this is a binomial experiment. Now consider this scenario. You have a box with 5 blue and 3 red marbles. You draw a marble, replace it, and then draw another. You do this a total of 5 times, and x is the number of red marbles drawn. Is this binomial? Let's check BINS again. Binary? Yes, you draw a red or a blue. Independent? Yes, because you replace the marble each time. Fixed number of trials? Yes, n equals 5. Same probability? Yes, the probability of drawing a red marble is always 3 out of 8. So, this is also a binomial experiment. Finally, let's change the last example slightly. You draw 5 marbles from the same box, but this time, you do not replace them. Is this a binomial experiment? Here, one of the BINS conditions breaks down. Binary, fixed number of trials, and independent trials are still met. But the probability of success drawing a red marble is no longer the same for each trial. If you draw a red marble on the first trial and don't replace it, the probability of drawing another red marble changes from 3/8 to 2/7. Since the probability of success is not constant, this is not a binomial experiment. Now that we can identify binomial experiments, how do we calculate their probabilities? We can start with a visual tool, the probability tree diagram. Let's use the spinner example from your notes. It has 3 blue sectors and 1 white sector. We'll spin it 3 times and define success as spinning a blue, so P is 3/4. We can build a tree diagram to show every possible sequence of outcomes. The first spin can be blue with probability 3/4 or white with probability 1/4. The second and third spins branch off in the same way. The independence of the spins means we can multiply probabilities along each path to get the probability of that specific outcome. For example, the path BBB has a probability of 3/4 cubed, which is 2764. The outcome BWB has a probability of 3/4 times 1/4 times 3/4, which is 964. Now, let's find the probability of getting exactly 1 blue spin, which is P key x 1. We need to find all the paths with exactly 1 B. These paths are B to W, W, BW, and WWB. You'll notice that the probability for each of these sequences is the same, 34 times 1/4 squared, which equals 364. To find the total probability of exactly one blue spin, we add the probabilities of these mutually exclusive paths. We have 3 identical terms, so it's 3 times 364, which is 964. The important takeaway here is that there were 3 ways to get the same number of successes and failures. The fact that there were 3 ways to get the same number of successes and failures is no coincidence. It leads us to a more general formula that is much more efficient than drawing tree diagrams. The binomial probability mass function, or PMF, is the core of the binomial distribution. It allows us to directly calculate the probability of getting exactly x successes in n trials. The formula is P of x equals n choose x times P to the power of x times Q to the power of n minus x. Let's break this down. The first part, n choose x, is the binomial coefficient. It represents the number of different ways to get x successes in n trials. It answers the question, in how many combinations can these successes occur? The middle term, P to the power of x, is the probability of achieving x successes. Remember, P is the probability of one success, so for x successes, we multiply it by itself x times. The final term, Q to the power of n minus x, is the probability of having n minus x failures. Since we have n total trials and x successes, the remaining trials must be failures. So the formula is the number of ways to arrange the successes, multiplied by the probability of those successes happening, multiplied by the probability of the corresponding failures. Now let's look at the notation you'll see in problems. If a random variable x follows a binomial distribution, we write it concisely as x is distributed as BNP. The tilde symbol means is distributed as. So x tilde b of np is the standard notation. Let's practice using the formula with an example. An archer has a 90% chance of hitting the target with each arrow. She fires 5 arrows. We want to find the probability that she hits the target exactly twice. First, let's identify the parameters. N, the number of trials, is 5. P, the probability of success, is 0.9. And since we want exactly 2 hits, x equals 2. Now we substitute these values into our PMF formula. P of x equals 2 is 5 choose 2 times 0.9 squared times 0.1 cubed. We calculate each part. 5 choose 2 is 10. 0.9 squared is 0.81, and 0.1 cubed is 0.00. Multiplying them together, we get 0.081. Therefore, there is an 8.1% chance the archer will hit the target exactly twice. This process of identifying n, p, and x, then plugging into the PMF, is the standard method for solving these types of problems. Sometimes, we are interested in a range of outcomes. For this, we use the binomial cumulative distribution function, or CDF. The CDF is used to find the probability that a binomial random variable is less than or equal to a certain value. Let's continue with the archer example. What is the probability that she hits the target at most 3 times? This is the same as finding P of x less than or equal to 3. This probability is the sum of the probabilities of getting 0, 1, 2, or 3 hits. While we could use the PMF formula for each of these 4 values and add them up, this is a tedious calculation. This is where calculators become extremely useful. Modern graphics calculators have built-in functions for both the PMF, point probability, and the CDF, cumulative probability. You'll typically find them in the probability distribution menu under names like binomdif and binomc. For the PMF, you use PDF. For the CDF, you use CDF. For our problem, to find P of x less than or equal to 3, you would use binomCDF with the parameters n at 5, p 0.9, and x 3. The calculator provides the answer directly. It's important to be able to use your calculator efficiently for the IB exam. This will save you a lot of time. Just a critical note for your exams. It is unacceptable to only write down the calculator function. You must always clearly state the distribution you are using, its parameters, and the specific probability you are calculating. Then you can show the function as part of your work. For our Archer problem, we would write, let x out b5, 0.9. We want to find px2 equal binom pdf 5, 0.9 to 0.081. This fulfills the rigor requirement. Beyond just finding probabilities, we often want to know the expected value and variability of a binomial random variable. The mean of a binomial distribution, also known as its expected value, is remarkably simple to calculate. It's given by the formula mu, or E of x, equals n times p. This makes intuitive sense. If you flip a fair coin 100 times, where n is 100 and p is 0.5, you expect to get n times p, or 50 heads. The expected value is the average outcome over a very large number of trials. The variance, which measures the spread or dispersion of the distribution, is also straightforward. The formula is sigma squared, or var of x, equals n times p times q, where q is 1 minus p. The variance is the average squared distance of each outcome from the mean. The standard deviation, sigma, is simply the square root of the variance, and it gives us the typical distance from the mean in the original units. Let's apply these formulas. A fair die is rolled 12 times, and x is the number of sixes. Find the mean, variance, and standard deviation. First, identify the parameters. N is 12, P is 1/6, and Q is 5/6. Now for the mean. It's N times P, so 12 times 1/6, which is 2. We expect to roll a 6 about 2 times out of T. For the variance, it's N times P times Q, so 12 times 1/6 times 5/6, which simplifies to 5/3. And the standard deviation is the square root of the variance, which is the square root of 5/3, or approximately 1.291. This tells us the typical deviation we can expect from our mean of 2. Understanding how the distribution looks is also important. The graph of a binomial distribution shows the probability of each outcome. Let's explore this using the example of spinning our spinner with 3 blue sectors 3 times. Recall, M3 and P3, 4. Using the PMF, we can calculate the probabilities for each value of x from 0 to 3. P of x and 0 is about 1.6%. P of x01 is about 14.1%. P of x02 is about 42.2%. And P of x03 is also about 42.2%. If we plot these probabilities as a column graph, we see that it is skewed to the left. The highest probabilities occur at the higher values of x, which makes sense because the probability of success is 3/4, which is quite high. We expect more successes than failures. Let's consider what happens when P changes. If P were 0.5, the graph would be perfectly symmetrical, centered at the mean. If P were small, say 0.1, the graph would be skewed to the right, with higher probabilities at lower values of x. Now, let's keep P at 0.5 and increase the number of trials, n. What happens? As n increases, the number of possible outcomes increases, and the distribution becomes smoother and more bell-shaped. A remarkable result from probability theory, called the central limit theorem, states that for a large enough number of trials, a binomial distribution can be approximated by a normal distribution. This is a very powerful tool in statistics. Let's work through some additional examples to solidify our understanding. These will be at an HL level. Example 1. A new drug is successful in curing a disease 7% of the time. It is administered to 15 patients. What is the probability that fewer than half the patients are cured? First, let's define our random variable and its distribution. Let x be the number of patients cured. This is a binomial experiment with n-15 trials, and a success probability P0.7. So, x is distributed as B15, 0.7. The question asks for the probability that fewer than half the patients are cured. Half of 15 is 7.5. Since the number of patients must be an integer, fewer than half means 0, 1, 2, 3, 4, 5, 6, or 7 patients are cured. So we want to find P of x less than or equal to 7. This is a job for our calculator's CDF function. Using binom CDF with n+15, P0.7, and x7, we get a result of approximately 0.1089. Therefore, there is about an 11.9% chance that fewer than half the patients will be cured by the new drug. Remember to show your work like this on the exam. Let's tackle a more complex problem involving the concept of at-least probabilities. Example 2. A school volleyball team has 9 players. Each player has a 75% chance of coming to any given game, independently. The team needs at least 6 players to avoid forfeiting the game. Find the probability that the team will have to forfeit a randomly chosen game. First, let's define our random variable x as the number of players who show up. The parameters are n=9 and p=0.75. So x equals b9, 0.75. The team forfeits if fewer than 6 players show up. That means the team forfeits if x is 0, 1, 2, 3, 4, or 5. This is p of x less than or equal to 5. We can calculate this directly using the CDF. Binomial MCDF 9, 0.755. The result is approximately 0.0872. So there's about an 8.74 chance the team will forfeit any given game. This is our answer to the first part. Now for the second part. The team plays 30 games in a season. How many games would we expect them to forfeit? Here, we're not asking for a probability. We're asking for the expected number of events, in this case, forfeits. We can model this with a new binomial distribution. Let y be the number of forfeits in 30 games. The probability of a single forfeit, which we just calculated, is 0.0872. The expected value of y, e of y, is n times p. That's 30 times 0.0872, which is approximately 2.616. So, in a season of 30 games, we would expect the team to forfeit between 2 and 3 games. A common IB question involves applying transformations to random variables. Let's explore how the mean and variance change. Suppose x is a discrete random variable, and we create a new variable y by multiplying x by a constant a and adding a constant b. So y equals a times x plus b. How do the expected value and variance of y relate to the expected value and variance of x? The rule for the expected value is that the expected value of y is a times the expected value of x plus b. This is a very intuitive result. If you double your expected score and add 5 points, your new expected score will reflect that change. The rule for the variance is a bit less intuitive at first. The variance of y is a squared times the variance of x. The additive constant b has no effect on the spread of the data. Think of it this way. If every data point shifts by 5 units, the spread between them remains the same. The multiplication by a, however, does affect the spread, and because variance measures squared deviations, it multiplies by a squared. This rule applies to any discrete random variable, including binomial ones. Let's apply this to the final example in your notes. A random variable x has a mean of 6 and a standard deviation of 2. Let y equal 4 times x plus 3. Find the mean and standard deviation of y. First, the mean of y. It's 4 times the mean of x plus 3. That's 4 times 6 plus 3, which gives us to 7. So the mean of y is 7. Now for the standard deviation of y. We can't find it directly from the standard deviation of x using a simple rule for the standard deviation itself. Instead, we use the rule for the variance. First, we need the variance of x. It's the standard deviation squared, so 2 squared, which is 4. Next, we use the variance rule. The variance of y is 4 squared times the variance of x. That's 16 times 4, which is 4. Finally, the standard deviation of y is the square root of its variance, which is the square root of 64. That gives us 8. The standard deviation of y is 8. So we found that the new random variable y has a mean of 7 and a standard deviation of 8. This is a very common HL-level application of these transformation rules. Let's summarize what we've covered today. We started by defining the 4 bins properties of a binomial experiment: binary, independent, fixed number of trials, and same probability of success. We learned that the probability of getting exactly x successes in n trials is given by the binomial probability mass function. We also saw how to use the binomial cumulative distribution function on our calculators to find the probability of a range of outcomes. And we learned to always state the distribution and probability clearly in our working. Finally, we derived the simple formulas for the mean and variance of a binomial distribution and applied the rules for linear transformations to solve more advanced problems. These tools are powerful for analyzing a vast number of real-world scenarios. To reinforce your understanding and prepare for your IB exams, here are 5 practice questions. I encourage you to pause the video after each question and try to solve it on your own before watching the solution. This active learning approach is very effective for mastering these concepts. Question 1. The probability of a certain type of seed germinating is 0.8. A gardener plants a row of 20 seeds. What is the probability that exactly 16 seeds germinate? Pause here and try to solve it yourself. Let's work through the solution. This is a binomial problem. Let x be the number of germinating seeds. Then x was 26, 0.8. We want to find p x 16. Using Binomial PDF, we get approximately 0.218. So there's about a 21.8% chance that exactly 16 seeds will germinate. Question 2. In a large population, 15% of people are left-handed. A random sample of 12 people is selected. Find the probability that at least one person in the sample is left-handed. Pause the video here to work on this one. Solution. Let x be the number of left-handed people in the sample. X is distributed as a binomial with n equals 12 and p equals 0.15. We want the probability that x is greater than or equal to 1. A useful strategy here is to use the complementary event. The probability of at least 1 is 1 minus the probability of 0. The probability that x equals 0 is approximately 0.142, so our answer is 1 minus 0.142, which is 0.858. There's an 85.8% chance of having at least one left-handed person in the sample. Question 3. A fair die is rolled 60 times. What is the expected number of times a 5 is rolled? What is the standard deviation of the number of 5s rolled? Pause and try calculating the mean and standard deviation. Solution. Let x be the number of 5s rolled. X is distributed as pica by 60 pasas. Test. The mean is NP, which is 60 times 1/6, or 10. The variance is NPQ, which is 10 times 5/6, or 25/3. The standard deviation is the square root of the variance, the square root of 25/3, which is about 2.89. So, we expect 10 5s, with a standard deviation of about 2.89. Question 4. X is a binomial random variable with n tau 10 and p 0.04. Find the value of p of x greater than 3 but less than 7. Pause and think about how to use your calculator for this interval. Solution. The condition greater than 3 but less than 7 means x can be 4, 5, or 6. We want to find px6 minus px3. This is binom CDF or 10, 0.46, minus binom CDF or 10, 0.43. Calculating these gives approximately 0.945 minus 0.383, which equals 0.562. There's a 56.2% chance that x will fall within this range. Final question, number 5. Let x be a discrete random variable with mean 4 and standard deviation 3. Let y equal negative 2x plus 10. Find the mean and variance of y. Take a moment to apply the transformation rules we learned. Solution. The mean of y is negative 2 times the mean of x plus 10. That's negative 2 times 4 plus 10, which equals 2. For the variance of x is the standard deviation squared, 3 squared, which is 9. The variance of y is negative 2 squared, times the variance of x. That's 4 times 9, which is 36. Notice that even though we multiplied by a negative number, the variance of y is positive, because the coefficient gets squared. That brings us to the end of our session on the binomial distribution. You should now be confident in identifying binomial experiments, constructing their probability mass functions, and calculating key statistics like the mean, variance, and probabilities over intervals. The binomial distribution is a powerful and versatile tool in statistics, and you will see it applied in many different contexts. Keep practicing these types of problems, and you'll be well prepared for your IB exams. Thank you for watching, and good luck with your studies.